This is How to Math with Dr. Ian Lundholm. In today's episode, Orthogonal Diagonalization. Oh, we are getting there, guys. This is section 8.2, and the only one that we have left after this is 8.6. So we're getting close to the end of the semester. I do have what will hopefully be a relatively short project for you and a final exam in the works. Hopefully I've already sent you an announcement about those things. If not, I'm sorry and thank you for being patient with me. Anyways, on to section 8.2, which is all about orthogonal diagonalization. Real quick, we'll remind you what the definition of an orthogonal matrix is. It's a matrix whose inverse is equal to its transpose. And as we will see shortly, an orthogonal matrix also has, some other important properties. Just by the fact that, this orthogonal matrix is acting as its own transpose means that something like A transpose A equals the identity matrix. And if you think about what that looks like column by column, here, let's say this one's A transpose, where we've got the first column of A kind of hanging out on its side all the way down to A and down here. So, yeah, those are the columns of A, or the rows of A transpose. Let's write A here. A1, A2, da, 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 AN. Those are the columns of A, right? And so what this means when we're multiplying these two together, now we can use the language of dot products. This first entry here correlated to this first row and this first column is A1 transpose times A1. And if this matrix is going to work out to be the identity matrix, that entry is going to be 1, right? And so one thing that we know, this is going to happen, with all of those different entries along the diagonal, it would be the same for A2 as well. All of those dot products are going to be equal to 1, which means all of the columns have length 1. Yeah, because what we're finding with that A1 transpose A1 dot product is really the square of the length of A1. So, yes, all of those columns have length 1, and if we're getting zeros, come on. There we go. All around here, up, up, above and below the diagonal, that means that all the columns are orthogonal. To each other, right? Because all of the dot products between columns that are different are 0. And those are two big properties of an orthogonal matrix that we can now talk about because we understand things like dot product and the lengths of vectors. So the columns of an orthogonal matrix form an orthonormal set. All right, continuing on. Get out of here, please. Right, and here are a couple examples of an orthogonal matrix. Yeah, A is orthogonal, the rows are orthonormal, and the columns are orthonormal. Those are definitely equivalent statements. I kind of just showed you how I understand that to be. And here again, they're showing you that the dot product of each of these columns is 1 when it's the dot product between the column and itself, and it's 0 when you're doing the dot products between different columns. Moving on. Okay, this will be our first example that we look at, and we're going to get into GeoGebra on this one. This matrix has orthogonal columns, but the rows are not orthogonal. We can verify that. Well, let's go to GeoGebra. Here are the columns of that matrix as vectors. Notice that they do, they're all perpendicular to each other. But if we, take the transpose and look at that matrix, the matrix's columns, look at the rows rather than the columns, the pink vectors are the rows that correspond, to that matrix. And you can see that the pink vectors are not orthogonal. They're not all perpendicular to each other. But if we take our original column vectors and normalize them, meaning that we make them of unit length, and we zoom in, now these vectors are of unit length, still heading in the same direction as the columns used to be. If we then look at the rows, the rows are now orthogonal. It's almost like magic. But really, what's going on here is, since we have normalized those original columns that we started with, here, let me go ahead and click one more. Please. There we go. Since we've normalized the columns that we started off with, we now have an orthogonal matrix. We've got a matrix that when you multiply it with its transpose would give you the identity. And so essentially the row vectors, the transpose of A is the inverse of A. Well, okay, of A prime. This is A prime. So yes, A prime transpose is the inverse of A prime. And so, the inverse of an orthogonal transformation definitely needs to be orthogonal to get everything back to where it used to be, if you're, actually taking the inverse of that transformation. So it actually makes a lot of sense, but that's pretty cool. All you have to do is normalize the columns here to give yourself an orthogonal matrix. And orthogonal matrices are really nice because when you multiply by orthogonal matrices, you don't stretch and skew space. All you really do is rotate it in some kind of a way. So orthogonal matrices, you can think of them as rotations of space. And that's, if you saw what I did for wonderful Wednesday with the toilet paper thing, I was using an orthogonal matrix there so that the toilet paper roll stayed the same size and the same shape throughout the transformation. Yeah, okay, we've already said that. Sure. All this is saying is that when you multiply two orthogonal matrices together, the product is orthogonal. And if you think about that as a transformation, if you rotate something and then you rotate it again, yeah, that would be another rotation. Or I guess you could maybe think of it as a reflection as well. Reflections are orthogonal. That's fine. So yeah, rotation or reflection, but we're not stretching or skewing space with orthogonal transformations. Cool. And yes, duh. Okay, cool. Here's where we get into the fun stuff for today. A matrix A is orthogonally diagonalizable if there exists an orthogonal matrix P such that P transpose AP is diagonal. So we've done this before with eigenvalues and eigenvectors, but this is the part this is the part that we've looked at so far, just with general eigenvalue, eigenvector relationships. We've said that P inverse AP equals a diagonal matrix D, or we've looked at it the other way, where the P and P inverse are playing similar roles over here, where it's A equals PDP inverse. We've definitely taken a look at that composition before, but now we're going to be able to make sure that P is an orthogonal matrix, which has some really, really nice, properties. Like we've said, it doesn't stretch or skew space. It's really easy to find the identity because all you have to do is take the transpose. And so orthogonally diagonalizing something is going to be preferable in all cases, if it's possible. And that is possible when we have an orthonormal set of n eigenvectors. And that happens precisely when A is symmetric. So that's the big thing. When A is symmetric, we are orthogonally diagonalizable. And these proofs are okay. I think the one that is the most interesting is this one. So the fact that, 2 implies 3. Let's go back here real quick. Why does a matrix being orthogonally diagonalizable imply that the matrix is symmetric? Let's go ahead and take a look at this one. Come on. Okay. So I guess I can... Oh my goodness. Sorry. We're supposing that the matrix is orthogonally diagonalizable. And by definition, that means that we have a way to decompose A so that it is PDP or PDP transpose. And if we take the transpose of, PDP transpose and distribute that transpose out to all of the individual PD and P transpose, we get PD transpose, P transpose there on the second line. And then since a diagonal matrix is always equal to its transpose, we get the third line, and that is A. And so we've really just proven that A equals A transpose, and A is symmetric. The other ones were even more boring than that. Anyways, the set of n orthonormal eigenvectors is called the principal axes of A. And here we go. We get to orthogonally diagonalize this matrix. Now, we know how to diagonalize a matrix, and the only additional steps that you'd need to add on to orthogonally diagonalize would be, first, you find the eigenvalues, right? So you calculate a characteristic polynomial based on the determinant of lambda I minus A. So characteristic polynomial first. In this instance, we've got two eigenvalues, 3 and negative 3, and the eigenvalue of 3 is repeated. So it has multiplicity 2. After that, we could find the null space of A minus lambda I by solving that homogeneous equation. Doing that for, the first eigenvalue, 3, we would find two different eigenvectors. Notice that right now, these eigenvectors are not orthogonal. If you took their dot product, you'd get 1 plus 0 plus 0, which is 1. So those are not orthogonal right now. And so they're going to be somewhat useful, but both of them can't be used to orthogonally diagonalize this matrix. Whereas, if we look at, the eigenspace related to negative 3, we've got 1, 1, 1. And actually, that vector is orthogonal to both of the first two eigenvectors. You could see that the dot product there is 0 in both cases. And that's not a coincidence. It's actually going to be true that when you have distinct eigenvalues, the eigenvectors corresponding to those distinct eigenvalues will be orthogonal with each other. Okay, so far, we have calculated eigenvalues, we've calculated eigenvectors. We have a set of 3 eigenvectors right now, but they are not all orthogonal, and they are not all unit vectors. So the next step will be using Gram-Schmidt and that algorithm to make sure that we have a set of 3 orthogonal vectors, and then finally we will normalize all those vectors to make sure they're of unit length. Okay, so here's here's the Gram-Schmidt orthogonalization. Notice that really it's only the second vector that changes. The first and the third vector were already orthogonal. It's really just that second vector that changes once you subtract the projection of, x2 onto x1. So now they are all orthogonal, and the final step would be to normalize them so that they're all of unit length. This gives us a matrix P that is an orthogonal matrix. And that's an orthogonal matrix full of eigenvectors. And yes, the diagonal matrix corresponding to this matrix P would be the one with the eigenvalues in it. Here's where things get fun. All right, hopefully I'm going to be able to pull this up. GeoGebra has been... Okay, I'm going to have to go to OneDrive. I'm going to have to get out of this. Orthogonal diagonalization. Open in another app. Doop. Copy to GeoGebra. I have a love-hate relationship with GeoGebra right now. It has been not cooperative in terms of saving its files and interoperability between my different devices. Ugh. Anyways, this is one of my most proudest creations. And I know it looks like there's a lot going on here, so let me explain what I'm thinking. Here we have three-dimensional space, right? And all of those dots are just in a grid, evenly spaced in three-dimensional space. And so it's just making a cube here. I made one face of the cube blue and one face of the cube red so that you can kind of track how those change as the transformation happens. And in light blue, you can notice that I have a plane here. That plane is related to the eigenspace determined by the eigenvalue 3. So yeah, that plane is all of the different linear combinations of the two basis vector, or the two eigenvectors corresponding to lambda equals 3. And then this line that goes through the corners of the cube corresponds to the eigenspace with lambda equals -3. And you can see that, yes, those definitely do look orthogonal right now. So those eigenspaces look to be perpendicular to each other. But what I want to do is watch this transformation a couple times and view it from the perspective of just kind of, a normal perspective where we're not paying attention to the eigenspaces necessarily, and then look at it as we're looking onto the eigenspaces. And it's going to be really cool to see what happens in terms of all space. So I'm going to play this first. This time, just be paying attention to, how all the dots move. How do the blue and the red squares move in space as this transformation goes on. All right. Ooh. That was interesting. So, yikes. It looks like space is expanding somewhat. It looks like things have changed orientation somewhat because now the red square is on top of the blue square. I'm going to zoom out a little bit. Rather than them being on different sides. So it's almost like, some kind of rotation has happened, but definitely some stretching and skewing as well. Here, let's watch it from a zoomed out view. Blue's on the left, red's on the right now. And it kind of looks like they squish a little bit. And yeah, keep moving. Maybe this isn't the best orientation because I was getting pretty close to looking at that one eigenspace. But yeah, okay. That's cool. We see all the dots kind of moving around together. Come on, GeoGebra. Let me pull the slider back. Okay. So that's one perspective, and you kind of see the red and the blue squares change positions. One goes on top of the other somewhat, and they all grow. Okay. Now let's take a perspective that is looking directly down on the plane. So right now, we're looking down on the eigenspace related to lambda equals 3. Ready for this? This is the same thing. I haven't changed the demonstration. But if I play it, nothing happens. That's not what I wanted to happen. Come on! There we go. In this view, we don't see any rotation, stretching, skewing, anything like that, all we see is growing. And we're precisely growing by a factor of 3 because this eigenspace has an eigenvalue of 3. So I think that this is super cool to be able to look from this perspective and just see how the eigenspace related to lambda equals 3 just grows throughout this transformation. And literally all I have to do is knock it off the axis a little bit to just show you that, yes, it is the entire space that is moving throughout this. But when you look at it precisely from that view, you just see everything growing. And it looks two-dimensional somewhat when you look at it this way. Okay, now for the other perspective, where we're going to try to aim ourselves so that we are kind of parallel with the plane, but perpendicular to the eigenspace related to lambda equals -3. So this is the starting off spot where we're still looking at a cube. Again, it kind of looks two-dimensional right now. But when we play this, you'll see that all the dots along that diagonal, change orientation. That's where the -3 part comes in. And then we are growing by a factor of 3 here. And even if you pay attention to the dots that were on that plane, you can see that those grow by a factor of 3 as well. So real quick, let me play that one for you again. Come on. Yeah. That's the eigenspace related to lambda equals -3. Anyways, I think that, I don't know, this demonstration is one of the most beautiful things that I get to look at in linear algebra. It's just really cool to understand how space moves via the eigen stuff that we've learned about. Anyways, that's orthogonally diagonalizing a matrix. Let's go back to the lesson. Boom. Cool. And so, yeah, that GeoGebra demonstration is, has links on Canvas. It's in our GeoGebra book. Okay, and that was kind of the climax of the lesson, and now we are in the falling action. A is a symmetric matrix. Then the eigenvalues of A corresponding to distinct eigenvalues are orthogonal. Yeah, I said that. This is actually a cool proof. So what's going on here is, suppose that we've got two different eigenvalues, lambda and mu. And lambda and mu are not equal to each other. And so they both have corresponding eigenvectors. X corresponds to lambda and y corresponds to mu. And then we look at this dot product. We can use properties of dot products to change this thing around. And hopefully all of these algebra steps should make sense, and they're all justified. But remember, yeah, we're looking at dot products here. The main way that we use the fact that A is symmetric is here at the last step. We've changed A transpose to A. So that now we've got X transpose AY minus the same thing, meaning that that side is 0. So what's interesting is that we figure out that that initial dot product was 0. Now, there's only, a couple ways that can happen. Either the eigenvalues are the same and that initial, scaling factor is 0. So that's not true because lambda doesn't equal mu. And so the only way that this dot product is actually equal to 0 is if x and y are orthogonal. And so that's a cool proof that shows you why that eigenvectors corresponding to distinct eigenvalues need to be orthogonal. Yeah, and this is just a summary of what we did in terms of orthogonally diagonalizing a symmetric matrix. It's find the eigenvalues, find the eigenvectors, use Gram-Schmidt to orthogonalize the eigenvectors that are not already orthogonal, and then scale everything down so that they're of unit length. Yeah. There's a little foray here into quadratic forms, which kind of deals with like conics. And I'll show you some of the pictures related to this, but it's not part of the core of what I want you to get out of this lesson. So this will be pretty brief. Here we have a conic, a hyperbola, just given by the multiplication of two variables. This is like x times y equals 1. Or y equals 1 over x, if you want to think about it that way. But when finding the principal axes of this, conic, this curve, you can create some new variables, y1 and y2. Notice that those variables give you a nice quadratic form that doesn't have any cross terms. And then y1 and y2 are the principal axes, that kind of show you the places where symmetry happens across that, that curve that you were given initially, that conic. And, in this example, those new variables y1 and y2 kind of just jump out of nowhere. But the idea is that you can find what those are by, some orthogonal diagonalization. So this is what it would look like to find the principal axes of this quadratic form. You can express that quadratic form as a matrix product where you've got a vector x transpose times a times x. And then you orthogonally diagonalize A in order to find the principal axes. So this is what that diagonalization looks like. And you can see here that, the way that you find those principal axes is at the end here, you're looking at the vector p transpose x as your new y vector. So that's cool. But again, not super important. But those would be kind of the lines of symmetry in that that conic. And again, here's just another example of the same thing. Boom. This is the last slide. Here we've got a theorem that they're calling the triangulation theorem. I'm going to do this so that I can start drawing and the drawings don't fade away. A lot of times you will hear this theorem called Schur's theorem. And what this says is that we've got a matrix, a square matrix with n real eigenvalues. Yeah, don't be confused. This wording is, I don't know, a little bit confusing. Really, we just have a square matrix. It does not necessarily mean that we have n distinct eigenvalues. We just have n eigenvalues, and that happens for any square matrix. It's okay to have repeated eigenvalues, all that kind of stuff in Schur's theorem. But what this says is that there is an orthogonal matrix P such that P transpose AP is upper triangular. And yeah, one of the things that actually is mentioned down here is that since the matrix P is orthogonal, P transpose is really P inverse. And so everything that we've talked about with similarity applies here. In a very succinct way of saying this is that any matrix A is similar to an upper triangular matrix. And that has some interesting consequences regarding its eigenvalues. So the corollary here, gives us two different interesting results. One of them is that the determinant of A is equal to the product of the eigenvalues. And that knowledge can be really handy a lot of times. Yeah, if you're doing, I don't know, matrix computations, if you're trying to get at the eigenvalues of a large matrix, that fact can be handy in algorithms that are kind of iteratively estimating eigenvalues. If you know the product, then you're able to error check and stuff like that. Also, the trace of the matrix, which is just adding up the diagonal entries, is the sum of the eigenvalues. And so this is just with any square matrix A. We have those two facts because we know that all square matrices are similar to an upper triangular matrix. And when two matrices are similar to one another, they share eigenvalues. All right, so that's section 8.2. Yeah, keep up the good work on the homework. Hopefully I've given you some instructions on what our project regarding the singular value decomposition will look like and what our final exam will look like. But that's going to take up, this Friday and all of next week is, that's what we'll be working on, those two things. And that's how we're going to wrap up the semester. So that is all for today's lesson, and I'll see you in the next one.